Yeah. After today's lecture, we finish module 1, and based on our schedule, we need to do our quiz number 1 this week. Yeah. So I plan to give it to you tomorrow, Friday. Yeah. So Friday, you will see quiz number 1. All right. Yeah. 10 questions. Yeah. Just remind you. Yeah. All right. Pen color change. Okay. All right. Yeah. All right. The topic, optimality problem. Yeah. So let me use one simple example to explain this problem. Yeah. D.1, minimum selection problem. First, let me describe this minimum selection problem. Yeah. Then after that, then we look at the optimality problem. Yeah. Our computing problem number 3, find the minimum of an array. A simple question, right? Yeah. Yeah. So let me just give you the description first. Given an array, our usual representation of an array, the question, find the minimum find the index I such that A of I is the minimum of the array. Simple question. Okay, yeah. So I believe most of you can solve this problem. Yeah, but there are a lot of interesting things we need to discuss here. Yeah. First, we have another basic problem type. The last time I gave you the search type, right? Search type. Yeah. The first one in this class, the basic type. This one, the second basic type. Yeah. So what type? Selection problem. Yeah. So later I describe the general selection problem. All right. Yeah. Here, the general selection problem. Yeah. Find the kth smallest element in a given array. That's simple. Yeah. One sentence, you get a general selection problem. Yeah. All right. And the minimum, that's a special case. So here, yeah, let's look at the special case. Finding the minimum, that's just the special case when k equals 1. The first smallest element. Yeah. Maximum, another special case with k equals n, the nth smallest element in a given array. The last one, yeah. If we sort the array, the minimum is the first element in the sorted array. Max is the last element in the sorted array. Yeah. But here, in this question, we should not sort array. Keep in mind, yeah, here, let me write it. Yeah. We should not sort the array. The reason, because it is too expensive. Too expensive. All right. Yeah. So that's the reason. Yeah. All right. Yeah. Let me give you the reference. Yeah. Yeah. In the textbook. Yeah. These two sections. Yeah. You can study. Yeah. Yeah. But here, let me describe the solution completely. Yeah. Actually, usually, although you have the material you can find in a textbook, but in my notes, I expand the material a lot. Yeah. So actually, what you learn from my notes much more than in our textbook. Yeah. All right. Let's do the work and analysis. Yeah. All right. I think most of you know the solution. Here, I just describe the solution. Yeah. Because the main point is not at the solution. The main point is the next step after the solution. Yeah. So for the solution, let me quickly go through the solution. First, we do initialization. Yeah. We create a variable called min. Yeah. min, and we assign its initial value, the first element of the array, a of 0. Yeah. After that, then we do iterations. Yeah. We run a for loop to do iteration. Yeah. All right. The general step for each iteration, we compare the min value with the current element, a of I. When we do that comparison, we have these two cases we can consider. The first case, the min is greater than a of I. In that case, that means a of I is smaller than the current min value. We should replace it with the current value. Okay, yeah. So we do one assignment operation. We assign a of I to that min variable. Yeah. So that's for the first comparison result. Other than that, otherwise, the remaining equal, smaller than, we combine as one case. Yeah. We do not want to separate equal and smaller than. Yeah. In that case, we should continue our for loop. Okay, yeah. Move to the next round of comparison. Compare min and a of I plus 1. Okay, keep doing this kind of iterations until we reach the end of the array. That is I equals the index of the last element, n minus 1, and we finish the iteration and return the value, min value, for this function. Now, that's the whole solution. Okay, yeah, very easy to implement. Yeah. All right. The question, we want to do some interesting discussion after the solution. Yeah. First, let's look at the number of comparisons. How many comparisons do we need? Yeah. When after you look at the solution here, can you quickly find the answer? The number of comparisons we need, you only count the number of comparisons. You do not count other operations like assignment, right? Yeah. So here we do not count assignment operation. Yeah. Just a number of comparisons. Any of you? Yeah. You may have a, you can guess. Okay, yeah. All right. N minus 1. Yeah, surely. N minus 1, good. Yeah. First, it's a correct answer. I want to see if any of you want to choose N. Okay? Another possible N. But N minus 1 is correct answer. Yeah. But the question is, yeah, here, let me put a correct answer here, a minus 1. The question is, how do you know it is a correct answer, right? How do you convince people this n minus 1 is the correct answer? Yeah, so that's the question. Yeah, here, let's try to understand. Yeah, so the question. Yeah. The question, why this answer is correct? Okay, yeah. We want to explain. We want, let's say, we want to convince people it is correct, right? You need to convince people it is correct. Yeah, so let's do that part. Yeah. Here, because remember last time when we worked on that polynomial evaluation problem, I introduced a simple counting technique called counting by reference. Yeah. So let me recall that method, counting by reference. Yeah. Here, I can use this method to convince people n minus 1 is correct. Yeah, let me show you. So let us practice another time this simple counting methods. All right. Let me draw this straight line, represent this array. We have n elements in this array, right? So the first one, I use little a0, a1, a2, and so on. Okay, yeah. The last one, a sub n minus 1. Okay, yeah. Here, when we count the number of comparisons, we use these elements as the reference to do the counting. Okay, all right. For the first element, it is an assignment, right? Main equals a of 0, and we do not do comparison. So for the first assignment, yeah, no comparison here. For the first element, okay, yeah. But after that, each iteration, we compare main with the current element, with A1, A2, the general AJ, and the last one with A sub n minus 1, right? So each element after the first one, we need to do one comparison. Okay, so that's our observation. Yeah. Now, we make our conclusion. Now, when we count the number of comparisons, the first one, because no comparison, we do not count it. After the first one, each element, we count one comparison, one comparison, one comparison. All right, one-to-one correspondence, right? Now, that's the counting by reference. We establish that one-to-one correspondence. One comparison corresponds to one element after the first one. That one-to-one correspondence. Yeah. Now, when we count the total number of comparisons, we just count the total number of elements after the first one. That's n minus 1. Okay, yeah. Because we do not count the first one. Okay, so n minus 1. Yeah. So this is a simple example. Yeah. All right. Next, our next discussion. Yeah. How do you know our solution is the best? Or another question, can we improve the solution? Yeah, so here, let's ask another question. Can we improve the solution? Right? Yeah. All right. Yeah. In other words, is it possible we can use n-2 comparisons to solve this problem? We just reduce our comparison number by 1. All right. Is it possible to find another solution that we only need n-2 comparisons? That question. All right. Yeah. Yeah. So the answer is 2 possibilities, yes or no. Right? Yeah. Yes or no. Yeah. So the answer, 2 possible answers, yes or no. Okay. If it's possible, n-minus possible, then we should take that better solution, right? Yeah, if it's possible. If no, yeah, you may have a possibility there is no chance to find a better solution. The answer is no. If it is no, that means our current solution is optimal. Okay, that means the current solution optimal. Because the current solution is already the best, it's optimal. There is no way to improve it. Right? That's the title of this part, optimality. So our next topic or subtopic, we like to examine this optimality issue. Is our current solution optimal? Yeah. So our next discussion, we want to see if that solution is optimal or not. Okay, yeah, yeah. All right, yeah, 2 options. First one, improved algorithm. We may not be able to do that. All right, yeah. Then convince people that is already optimal. That solution, the current solution is already optimal. Now we need to do this. Second option. Yeah. So based on your intuition, we probably feel that n-1 is already optimal, right? Yeah. Nobody can improve it. Yeah. But how do you convince people it is optimal? That's the question. Okay. Yeah. All right. So let's do that part. Yeah. Optimality. Let us look at this general optimality issue. All right. The hard part. Yeah. There is something that's pretty. That's hard. Yeah. Okay. Yeah. So the hard part is, oh, yeah. So here, yeah, look at that. Because I click the admit button, yeah, then my remote control doesn't work. It happens a few times last time, last semester. I need to restart my, PowerPoint slides, all right, to make it work. All right. Yeah, so it works now. Yeah, yeah. All right. The optimality issue, there is a hard part. When you want to convince people our current solution is optimal, the hard part. What's the hard part? Among all the possible algorithms, how to show that this one is optimal? Yeah, because if you want to convince people this algorithm is optimal, you need to exhaust all the possible algorithms that can solve our current problem, right? You need to exhaust. Yeah. So the hard part is this. Well, I need to change parent color. Yeah, again. Yeah. Okay. Yeah. So the hard part is this word, exhaust. Is that possible? It looks like you need to exhaust, right? Yeah. By intuition, right? By intuition, you need to, consider all the possible algorithms. Yeah. But we know, oh, yeah, another one. Yeah. I'm happy to see new students join us. Yeah, but the only, oh, good. This time my remote control works. Okay. Yeah. All right. Yeah. The hard part is, yeah. So here, this exhaust. Let me write here. The hard part is when you consider all possible algorithms, you need to include those unknown algorithms. There are some algorithms unknown. Yeah. People have not developed those algorithms, right? There are some unknown algorithms, right? Yeah. Known algorithms, you cannot say all the algorithms have for finding the minimum of the array of an array have been developed. You cannot say that, right? So there must be some unknown algorithms. You need to include those algorithms. But issue is, how do you study unknown algorithms, right? They're unknown. How can you study those unknown algorithms, right? That's hard, right? Yeah. You will see we can study unknown algorithms. Although they're unknown, we can find a way to study those unknown algorithms. Interesting. Yeah, think about that. Okay, study unknown algorithms. Yes, we can. I will tell you the point. Yeah. All right. Question. How do you study unknown algorithms? Yes. The answer is, yeah. So is it possible to study unknown algorithms? The answer is yes. Yeah. The question is how? Okay. Yeah. Yeah. Let me tell you how. Right. Yeah. How to study unknown algorithms. Yeah. Here, we need to convince people our current algorithm is optimal. Then we need to cover all those unknown algorithms. Yeah. I will show you how to cover. Yeah. We need some imagination based on our real world experience. Yeah. Here, yeah, I use some simple real world experience to help us convince people the algorithm is optimal. Yeah. Yeah. Comparison. Here, let us find something similar in the real world for that comparison. When we do comparison, okay, we bring two elements. We compare which one is larger, which one is smaller, right? That's the typical comparison. Yeah. But in the real world, we have the similar situation. Yeah. Here, I like to use our experience in a sports game. Yeah, in a sports game, right? Two players, they need to play each other, right? Yeah, a match between two players, right? Yeah. For a certain game. Okay, yeah. Because when two players, they have three possible results that correspond to three possible results for a comparison, for a match. Okay, two players, they are tied. That's equivalent to equal, right? Tie equivalent to equal. Okay. A player beats B player. That equivalent to A is greater than B. A lost to B, it is equivalent to A less than B, right? Yeah. So we use this kind of analogy to help us understand the optimality issue here. Yeah. All right. Yeah. So yeah, that one, the results, yeah, less than, but here, less than, yeah. When we get to the current problem, because our goal, find the minimum, that means the smaller the better, right? The smaller the element value, the better. Not the larger the better, right? Yeah. Because we're not finding the maximum. If we need to find the maximum, the larger the better, right? Yeah. Here, the smaller the better. So when we look at the less than case, yeah, A less than B, yeah, so here, let's consider A less than B, then A is the winner, right? Because the smaller is better, so we make A the winner, not B the winner, all right? A smaller, so we select A, not B, okay? Yeah, so we make that change. Equal, that's tie, the game is tie, yeah. Greater than, A is the loser, all right? Yeah, lose to B, yeah, all right. So that kind of analogy we can use for this optimality discussion. Then I try to convince you here, our current solution already optimal. Yeah. So let's start. Let me run this convincing argument. Yeah. All right. Yeah. A sequence of statements and see if it is correct or not. Yeah. If you feel any statement is incorrect, you can argue with me. All right. Yeah. All right. The first argument. Yeah. Imagine that main is the final winner. Yeah. So when we start our discussion, yeah, so here we just set up, right? So this step is as the setup. So let us assume this main is the final winner. Okay, final winner, the minimum, right? The minimum is the final winner. Okay, yeah, yeah. And here, the final winner, we are in the sports game context, the final winner. All right, yeah, sports game context. Yeah, all right. Next statement. The final winner needs to beat all the other elements in the array. Yeah, all the players in some tournament, right? Yeah, through comparisons, directly or indirectly. Yeah, here I need to explain this part. Directly, that's easy. A beats B. That A beats B directly, right? But A can beat B in an indirect way. Now, so let me explain this indirect way. Yeah. Here, let's consider A less than B and B less than C. All right. Yeah. That means A beats B and B beats C. But A and C, these two players, they do not play directly. Okay. Yeah. But can we conclude that A less than C? Yeah. In math, we can do, right? In math, for the inequality, there is a property. Yeah. The property we call a transitivity property. Transitivity, yeah, it's correct. Property. Transitivity property in math, all right? So here you can see if we make analogy in the sports game, yeah. A and C, they do not need to play. We can save a game. Yeah, they do not need to play. So we, based on the transitivity rule, right? In math, we have transitivity rule. In the real world, we may not have. Here, in the real world, we do not have transitivity rule, all right? But here, we come from math comparison. All right, math comparison. So we have the transitivity rule. Yeah. So based on our transitivity rule, we have A less than C. Yeah. That means A beats C indirectly. That's okay. So A and C, they do not need to play. They do not need to compare each other. We can save one comparison. In this way, we can save one comparison. All right, yeah. Okay. Next. Yeah. Next. If an element loses once, it is eliminated. Now, think about if an element loses once, it cannot be the minimum, right? Now, loses once, that means it is not the smallest. Okay? Yeah. Then we do not need to consider it anymore. That is, we can eliminate that loser element out of the consideration, right? Yeah. Okay. Yeah. So this statement also correct, right? Yeah. Next statement. Each comparison can only eliminate one element. Can you eliminate more than one by one comparison? Each element you can only eliminate that loser, right? How can you eliminate the winner? Think about that. You cannot eliminate the winner. You can only eliminate the loser. So each comparison can only eliminate one element. Or we say can only eliminate at the most one. How about that? More precisely, we say it can only eliminate at the most one because it can eliminate zero. Why? You beat a loser twice. Think about that, right? You may beat a loser twice because if a loser is beaten once, it should be eliminated. But you may make a redundant comparison. You compare that loser with another new element, and that new element is the winner. So you beat that loser twice, right? Yeah. So here, more precisely, we can say each comparison can only eliminate at the most one element. It could be zero, okay? 0 or 1. Yeah. 0 or 1 for the elimination. Okay? Yeah. The next statement. Then the last statement. Because in order to find the final winner, we need to eliminate n-1 elements, right? In order to eliminate n-1 elements, we need at least n-1 comparisons, right? Each comparison can only contribute one elimination, right? At the most one elimination. So in order to get total n-1 eliminations, you need at least n-1 comparisons, right? That's the last argument. Okay, last statement. Yeah. So if you feel all these statements are correct, then we get the answer that n-1, our current solution, that's the best one. You cannot do better than that. Or nobody can do better than that. Yeah. Even we know there are so many unknown algorithms, but still, for those unknown algorithms, you cannot do better than this n-1. Think about that. Think about that. Here, our argument, our convincing argument, we cover all those unknown algorithms. We cover them, right? No exception. We cover all the possible algorithms. Yeah. So here, why we can cover, yeah, because we find a property covering all those algorithms. All right, yeah. Find a property. Property. So what's that property? What's that property? Elimination property, right? Yeah. The winner eliminates n minus 1 elements, that property. Okay? Yeah. So that elimination property. Elimination property. Okay? Okay? Yeah. Main, yeah. The winner eliminates n minus 1 elements. Okay, this property is true for all algorithms for finding the minimum, right? So this property is correct for all algorithms finding the minimum element, including those unknown algorithms. Okay, now you have millions of different ways to solve this problem, but this property, common property, covers all of them. So we use this common property, so we convince people our current solution is optimal. How about that? How about that? Okay, yeah. So you can see we can make it. We can answer that optimality question in this way. Yeah. All right. Yeah. And here, in this part, I talk about elimination many times in our discussion. Yeah. So I like to, yeah, emphasize this elimination idea. Okay. Elimination method. Later, we will use this method many times. Yeah, here, it is the first time we apply the elimination thinking idea or method in our discussion. Yeah. So this method is very powerful, or this thinking is very useful. Yeah. In this class, we will use many times. All right. Any question? Yeah, we'll finish optimality issue, question, discussion. Yeah. All right. So if no question, I just move to the next topic. Yeah. If you have any question, you just type in the chat area so I can see it. Yeah. Otherwise, let me move to the next topic. The next topic, I like to give you a few examples. So I call comprehension question, step number 1. Yeah. I show you a few questions. Yeah. There's some of the questions, not easy to answer. Yeah, because, pretty tricky. Yeah. All right, the first question. Yeah. True or false? Yes. True or false? The statement, algorithm can be optimal because one can always improve a given algorithm. Think about that. We just finished the discussion. We solved the problem. After that, I ask you this question immediately. Yeah, let me repeat that statement. no algorithm can be optimal. Why? Because one can always improve a given algorithm. There is always some room to improve. Yeah. It sounds reasonable, right? By your intuition, but we just complete our argument, optimality argument in our previous example. Okay, yeah. So the answer is false because our finding the minimum, so that algorithm is optimal. We prove that. Okay, yeah. All right, so here, one can always, because this part, this sentence part, this is by intuition. Why you make the statement? Because people by intuition, right? Yeah, people make their statement most of the time by intuition. Yeah. But we know the intuition could be wrong. Could be wrong, right? Yeah. You cannot guarantee your intuition is correct. Actually, the chance for people's intuition to be wrong is pretty high. Okay, it's pretty high. Yeah. So, all right. Yeah. All right. Yeah. So that's the first question. Yeah. All right. The next second question. Yeah. Nobody can show that certain algorithm is optimal because you cannot exhaust all the algorithms for solving a particular problem. Related to our discussion before, right? Yeah. Yeah. Let me read this statement another time. Yeah. Try to think about. Nobody can show that certain algorithm is optimal. Why? Because you cannot exhaust all the algorithms for solving a particular problem. Look at the because part. Now, the reason, look at this part. You cannot exhaust. That's correct, right? Nobody can exhaust. So this part, correct. Okay, yeah, correct. You cannot exhaust. But even if it is correct, the deduction is wrong. Okay, yeah. So here, question: even if this because clause, even if it is correct, okay, yeah, but that deduction is incorrect. Okay, why? Yeah. So here, I try to trick you. I make this question. I try to trick people. Yeah, confuse people. If you really understand the concept well. Yeah. So that's the reason I designed these two questions. Yeah. All right. So let me explain. So, yeah. So this time the intuition is correct. Nobody can exhaust all algorithms for solving a particular problem. Yeah. Intuition is correct, but deduction is wrong. All right. That's another type of error. Deduction is wrong. Yeah. So why the deduction? All right. So so the answer false first. Yeah. Why the deduction is wrong? I answered in the previous slide already. Yeah, so let me repeat that. Yeah. So here, let me write the explanation. Yeah. All right. So my explanation. Okay. Yeah. All right. Let me write a complete sentence here. Yeah. Although yeah, Okay, we cannot exhaust all those, yeah, I do not write detail, all those algorithms yeah. But we did it before, right? We did it in the previous example. Yeah. We can, yeah, sorry, we can, this time, we can find a common property okay, or some common properties, more than one, okay, that covers or, yeah, you know it, yeah, covers all those algorithms. That's what we did before, okay? That covers all those algorithms, the common property way, okay? And make the conclusion. Okay, so that's the way we can do it, okay? Without exhausting all the algorithms. We can convince people by using some common property. All right, yeah, the critical part is you need to find that common property. Okay, yeah, so then you can do it. All right, so that's the second question. All right, next question, number 3. Yeah. Given a polynomial with the form p of x, now this here I choose the highest degree equals 4, n equals 4 case. Okay, yeah. So the question, is it possible that one can find a special case? Special case here, I do not look at the general case. The special case means you can choose these values, A0, A1, A2, A3, A4. You have freedom to choose special values. Okay, you have that freedom. Okay, well, you have freedom to do that. The question, is it possible you can make the number of multiplications to evaluate this polynomial less than 4, strictly less than 4, all right? Strictly less than 4. If 4 equals 4, we can, by Horner's rule, equals 4, right? So here, we just learned, in part C, we just learned by Horner's rule. Horner's rule, the answer equals 4. But here, when you have the freedom to choose special coefficients, is it possible to beat Horner's rule? We can do better than Horner's rule. That's the question. Okay, yeah, think about that. Okay, yeah, a little tricky. Yeah, here for this class we have many questions. That's pretty tricky. Yeah, like this one. Yeah, All right. So here, let me give the answer, right? Because I do not have a lot of time. I need to move quickly. Let me give the answer. The answer is yes. It's possible. It's possible. But you may wonder, right? Why it is possible? Okay, why it is possible? All right, yeah. So here, all right, let's look at the possibility. Okay, here's number one. Because you give me a lot of freedom, right? You give me a lot of freedom, so I want to take advantage of that freedom. All right, yeah. All right. Oh, yeah. So here, oh, I need to add one more condition, yeah, to make it more rigorous, to make this question more rigorous. All right. A4 cannot be 0. All right. Otherwise, it won't be a degree 4 polynomial. Here we want to look at a true degree 4 polynomial. So A4 cannot be 0. Yeah, extra assumption add to this question. All right. So even that, other coefficients could be 0. Yeah. So here we use our freedom. We make A4 equals 1, but all the remaining coefficients be 0. Can we do that? Is it legal to take this kind of special value? Yeah, well allowed. In this question, we cannot see it is not allowed, right? Yeah. So we have that freedom. Yeah. So this is allowed if under this assumption, P of X, just simply X to the 4th, right? Yeah. X to the 4th. X to the 4th. How many comparisons do we, how many multiplications? 3 multiplications, right? Yeah. If you do the straightforward multiplication, X times X times X, 1, 1, 1, 3 here, right? Okay, less than 4, right? Yeah. So when you use the freedom of this freedom, you can get a better answer like this. Okay, yeah. So that's the first possibility. Yeah. All right. Second possibility. All right. So here I just, modify the condition. Yeah. Here I like to modify the condition. Right? So what's my new condition? Yeah. I add a new condition. Okay. Yeah. All coefficients are non-zero. How about that? Yeah. I do not allow you to, to make A0 through A3 all 0. I do not allow you to do that. Yeah. So I add another condition. All coefficients are non-zero. Then I ask you this question again. Is it possible? Right? Yeah. Yeah. The answer is still yes. Yeah. Even we under this new condition, the answer is still yes. Okay. Yeah. Why? Here, there is a smart trick. There is a smart trick here. All right. Yeah. Yeah, let me show you what is the smart trick here. Okay. All right. Here, I assume I take the polynomial, degree 4 polynomial equals 1 plus 4x plus 6x squared plus 4x cubed plus x to the fourth. This polynomial, right? Here I choose these special coefficients, 1, 4, 6, 4, 1, for these A coefficients. Then I claim I can use less than 4 multiplications to find the value of this polynomial. Can you see that? Can you see that? Interesting thing here. 1, 4, 6, 4, 1. Is anyone see a special pattern here? These coefficients, 1, 4, 6, 4, 1. Any special pattern? You can see here. Are you familiar with this pattern? Famous pattern? Yeah. All right. So let me explain this trick. All right. Yeah. This one equals 1 plus x to the fourth. 1 plus x to the fourth. But now, binomial formula. Do you remember this formula, binomial formula? Or Newton's formula? Binomial formula, Newton's formula. Yeah. In discrete math. So if you go back to look at your discrete textbook, if you can find this binomial formula. All right, yeah. And this pattern related to a very interesting observation called a Pascal's triangle. Pascal's triangle. Yeah, so you have this 1 plus x to the fourth. Then this 1 plus x, you do not need any multiplication, right? After you find 1 plus x, you raise to fourth, you only need 3 multiplications, right? Less than 4. Okay, less than 4 here. Yeah, because after 1 plus x, you raise it to fourth power, you just need 3 multiplications. All right, yeah. All right, so here, let me explain that famous Pascal's triangle. You can do some web search later when you study, when you go home, you can do some web search Pascal's triangle. Top, you put a 1 there. Yeah, you put a 1, that corresponds to 1 plus x to the 0th power. Okay, 1. All right. Then the triangle 1, 1. So this corresponds to, yeah, because 0th power, that's 1. All right. Here, 1 plus x to the first power. First, 1, 1. So 1, 1. Yeah. Next one, 1, 2, 1. That coefficient corresponds to 1 plus x squared. Yeah, because equals 1 plus 2x plus x squared. So the coefficients 1, 2, 1. Okay. Next one, 1. All right. 3. 1 plus 2, so 3. Adding 2 numbers on its shoulder, 3 and 1. Okay. Yeah. That corresponds to 1 plus x cubed. That is 1 plus 3x plus 3x squared plus x cubed. Then the fourth, 2 numbers on shoulder adding together, we get a 4. two numbers unsure adding up, 6, 4, 1. Okay, so that corresponds to the fourth equals 1 plus 4x plus 6x squared plus 4x cubed plus x to the fourth. That's what we need in this question. You can move down many levels, all right? Move down many levels. That is the well-known Pascal's triangle. Okay, yeah, very interesting. Yeah, see, yeah, if you have this background, then you can answer the previous question. If you do not have this background, then it is pretty hard, right? It is pretty hard. Yeah. All right. Next, we have a few minutes. Let me give you another question. Yeah. All right. Question. Yeah. Tricky, a little tricky, interesting question. Go back to our finding the minimum problem. We solved that. A simple problem, but that problem is very useful. So we solve it. Okay, all right. So given an array with n elements, and this n greater or equal to 3. Okay, the minimum is 3, at least 3. Okay, yeah. Question: how to find an element in this array that is neither minimum nor maximum. Okay, this question, yeah. Use smallest number of comparisons. Okay, think about this question. Given an array with n elements, at least 3, yeah, our n, how to find an element in this array that is neither minimum nor maximum. Your solution should be the best. The best means you use smallest number of comparisons. Think about this question. Okay, yeah. So here, let me do some discussion here. Okay, do some discussion. All right. Assume, you know, our array n elements, A0, A1, A2. Yeah, this is the given array. Okay, all right. Because we just learned finding the minimum problem, right? we have that solution, maximum or minimum. Solution basically the same, okay? Yeah, maximum or minimum, all right, okay, all right. You may think in this way, yeah. Finding the mean, you need n-1 comparison, right? Yeah, so Emerald, you get a mean, all right, yeah. Then, after you get a mean, remaining, because other than mean, remaining n-1 elements, right? Remaining, you have n-1 elements. In the remaining n-1 elements, how to find a max? To find a max, you need n-2 comparisons, right? n-2 comparisons. Yeah. But our goal, find the element that is not a minimum and not a maximum. Then you just find element that is not a min, not a max. Yeah. So anyone, yeah. So you will say, yeah. Now you do not choose min, do not choose max. Anyone in the remaining n-2, yeah, yeah, because we exclude min and max, right? Anyone in the remaining n-2 is a solution, right? In that way, you need this many comparisons, right? 2 n-3, okay? Yeah. So you have one solution that needs 2 n-3 comparisons. Now the question, okay, is this solution the best? You need to ask this question. Is the solution the best? Can you do better than this one? No. This is one solution. No. But it may not be the best one. Is it possible to use much fewer number of comparisons to find a solution? Right? Yeah, yeah. We almost run out of time. I only have 1 minute left. Let me tell you the answer. All right. The answer, the final answer, the best solution solve this problem, only 3 comparisons. Three comparisons. No matter how large is that n, only 3 comparisons for the best solution. And could be 1 million, 2 million, right? Yeah, no matter how large it is, the answer always 3 comparisons. Is that interesting? Think about that. How to use 3 comparisons to find the answer. That's pretty interesting. Okay, I leave that as, you know, some thinking question.